In this video, we're going to learn about convolution. I know that word sounds a little intimidating, but I promise it's one of those tools that once you see what it does, you'll really appreciate it. Let's start by talking about why we even need this. There are two situations where convolution is incredibly useful. The first is for evaluating inverse Laplace transforms like this. Sometimes you can factor this and use partial fractions, but sometimes using partial fractions doesn't work cleanly. This is where convolution comes in. Convolution allows us to rewrite a product in the S domain, making it possible to evaluate the inverse Laplace transform. A product in the S domain corresponds to something called convolution in the time domain. Here's a second situation where convolution is useful. In many applications, we often have a differential equation where the forcing function, the input f of t, is complicated or even unknown, and this makes solving a differential equation really difficult. Let me show you an example. Convolution can be used to solve an ODE like this with an unknown forcing function f of t by combining this input with the function determined by the ODE. In this ODE, that's the sine function, and then adding up their values over time to produce the solution y of t. At the end of this video, we will actually see how to find this solution. This solution is an integral solution, and it's called a convolution, and we're now going to take some time and understand what this is. Let's define convolution. The convolution of two functions f and g is defined by the integral here in this green box. This is called the convolution integral, and it's equal to f star g of t. That star is not multiplication, even though it looks like it is. Instead, it's a special operation, an integral that measures how the two functions combine as one is shifted across the other in time. Notice what's happening inside this integral. We're integrating over a dummy variable called tau, and tau goes from 0 to t. We plug tau into f and t minus tau into g, and then we multiply and integrate from 0 to t. The integral is essentially asking, how does the accumulated interaction between f and g build up? We'll see exactly what this looks like when we walk through some examples in just a minute. Here's the theorem that ties everything together. It's called the Convolution Theorem. This theorem tells us that the Laplace transform of a convolution of two functions is the product of their individual transforms. The Laplace transform of the convolution of f and g is just the Laplace transform of f times the Laplace transform of g. This gives us a new way to evaluate Laplace transforms when other methods are difficult or don't apply. Now let's read this the other way. This is the direction that we're going to use most. The inverse Laplace transform of a product f of s times g of s equals the convolution of f and g in the time domain. So instead of having a product in the S domain that we can't invert or is hard to invert, we move to the time domain and compute an integral. That's our new tool. Let's now walk through some examples. We're going to walk through two convolution examples. In the first example, we'll compute two convolutions, and in the second example, we'll use convolution to find the inverse Laplace transform of a product. In this first example, we want to find the convolution of f of t and g of t. In part A, we're given that f of t is 1 and g of t is t. Over here on the right, I've written down the integral that the convolution is equal to, and that's where we're going to start. The convolution of f and g as a function of time is equal to the integral from 0 to t, f of tau times g of t minus tau d tau. Let's now substitute in what f and g are equal to. F is equal to 1, and then g is equal to t, so g of t minus tau is just t minus tau, and we integrate with respect to tau. This gives us t times tau minus tau squared divided by 2, and then tau is equal to 0 up to t. Plugging in t, we get t squared minus t squared divided by 2, and then we subtract off our lower limit, and that's actually going to be 0 for each of these expressions. This gives us an answer of t squared divided by 2. Notice that our answer is a function of time. Let's now do one that's a little bit more complicated. We'll again start with our definition. The convolution of f and g as a function of time is defined to be the integral from 0 to t, f of tau times g of t minus tau d tau. Our function f is equal to t, so f of tau is just tau, and then we have g of t minus tau, and that's e to the t minus tau, and we're integrating with respect to tau. To evaluate this integral, we are going to have to use integration by parts. Let me put the formula over here. We have the integral of u dv is equal to uv minus the integral v du. We're going to let u be equal to tau, because du will just be d tau, and then dv is what's left, e to the t minus tau d tau. Our du is d tau, and then our v is going to be the integral of e to the t minus tau d tau, and that is minus e to the t minus tau. That minus comes because there is a minus in front of the tau. Let's now see what this gives us. We have u times v, so this is minus tau e to the t minus tau, and we're going to integrate from tau is equal to 0 to t, and then we subtract off the other piece. There's already a negative on this piece, so we have minus and negative, so we have a positive, the integral e to the t minus tau d tau, and we're going to integrate from 0 to t. Let's hold off evaluating this first piece because we can combine it with the next piece that we're going to get. And let's integrate the second piece. This integral is minus e to the t minus tau, and we're going to evaluate this from tau is equal to 0 to t. We can write this as minus tau plus 1 e to the t minus tau, and then tau goes from 0 to t. This is equal to minus t plus 1 e to the t minus t, so that's just e to the 0, minus a negative, so plus 0 plus 1 e to the t, and we can write our final answer as e to the t minus 1. When you compute convolutions, you end up using a lot of integration techniques that you learned in Calc 2. In this second example, we want to use convolution to evaluate the inverse Laplace transform of the following function, 1 divided by s times the quantity s squared plus 1. The function that we're given is the product of two functions. So we're going to write this as 1 over s times s squared plus 1 is equal to f of s times g of s. We can say that f of s is 1 over s and g of s is 1 all over s squared plus 1. The inverse Laplace transform of the product of two functions, f of s and g of s, is equal to the convolution of f and g, written f star g, of t. This convolution is equal to the integral from 0 to t. I have the formula up here on the right of f of tau times g of t minus tau d tau. Since we need to substitute f and g into this integral, what we're going to do now is actually find f and g. We have that f of s is 1 over s, and when we take the inverse Laplace transform of this, we get little f of t is equal to 1. G of s is equal to 1 all divided by s squared plus 1, and its inverse Laplace transform is little g of t is equal to sine of t. You can just get those from a Laplace transform table. Now let's put it all together. Our inverse Laplace transform of f of s and g of s is equal to the integral from 0 to t, f of tau, which is just 1, and then we have g of t minus tau, and because g of t is sine t, what we have here is sine of t minus tau, and we integrate with respect to tau. When we take the integral of this function, we get a minus that comes from minus tau, and then the integral of sine is minus cosine, so we have a minus cosine t minus tau, and we integrate this from tau is equal to 0 to t. The two negatives combine, and we just have cosine t minus t, so that's cosine of 0 minus cosine of t. So the inverse Laplace transform is equal to 1 minus cosine of t. Convolution provides a nice alternative method to using partial fractions to find an inverse Laplace transform. In this example, we're going to use convolution to solve an ordinary differential equation with an unknown or general forcing function. That forcing function f of t is what makes this interesting. We're going to start by taking the Laplace transform of both sides of the differential equation. In this green box, I put down the formulas for the Laplace transform of the derivative of a function. We're going to start by using this formula right here. Y double prime of t is s squared capital Y of s minus s times little y of 0 minus little y prime of 0. Those are our initial conditions, plus the Laplace transform of y, which is capital Y of s. And then on the right-hand side, we have the Laplace transform of little f of t, and that is capital F of s. In step 2, we are going to substitute in the initial conditions. Here are our initial conditions, and if we look back up top, these initial conditions are equal to 0. So this makes this nice. We're just going to substitute in that those are 0, and we get s squared capital Y of s plus capital Y of s is equal to capital F of s. In step 3, we're just going to solve this equation for capital Y of s. We can write this as s squared plus 1 capital Y of S is equal to capital F of S, and then we get capital Y of S is equal to capital F of S, all divided by S squared plus 1. In step 4, we're going to use convolution to take the inverse Laplace transform of Y of S to find Y of t. Little y of t is the inverse Laplace transform of capital Y of S. So this is the inverse Laplace transform of F of S all divided by S squared plus 1. And we're going to rewrite this and break up what's inside, and we're going to write it as the inverse Laplace transform of capital F of S times 1 all divided by S squared plus 1. Convolution tells us that the inverse Laplace transform of the product of two functions, capital F of S times capital G of S, is the integral from 0 to t, f of tau, tau's just our dummy variable, times g of t minus tau d tau. This function right here, over here on the right, is capital G of S. Notice that inside our integral, we need little g of t, or little g of t minus tau. So what we're going to do first is find the inverse Laplace transform of g of s. This is the inverse Laplace transform of 1 all divided by s squared plus 1. And you might recognize this. This is just equal to sine of t. Now we can go ahead and just write down our solution. Our little y of t is the integral from 0 to t, f of tau. That just goes in as f of tau, times g of t minus tau. G of t is sine t, so we're going to replace t with t minus tau, and we get sine of t minus tau, and we integrate with respect to tau. And this is the solution to our differential equation. No matter what f of t is, this convolution integral gives us y of t. That's the power of convolution. And that's it. You now know what convolution is and how to use it to find inverse Laplace transforms and to solve ordinary differential equations. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.